Okay, so let me say a few words to introduce the next plenary speaker. I'm very pleased to have Michael Hutchings giving the next talk. So Michael holds a PhD degree from Harvard University under Clifford Taubes, and he's done seminal work in many areas of geometry and topology, and his work is very broad, and it ranges from the study of soap bubbles and isoparametric problems, and in this context, he solved a very important conjecture, the so-called double bubble conjecture, to the development of very sophisticated techniques in symplectic topology and gauge theory, with applications to a very wide array of problems, including problems of dynamical nature, such as the existence of periodic orbits of Hamiltonian systems, or closed Reeb orbits of contact forms, which I think is the topic of his lecture today. So,
can you hear me? All right. Well, thank you very much for that very nice introduction and for the invitation to speak at this colloquium. The outline is first I'm going to tell you some basic things. What are Rave orbits and why are they interesting, at least to me? And then I'll state some theorems about the existence of Rave orbits and some questions. And I'll state the main theorem which I want to tell you about the two or infinitely many orbits. And then I'll talk about what's involved in the proof of this. And there are a lot of ingredients, so at least try to give you some idea. So what are Rave orbits? Why do we care? So let's briefly recall Hamiltonian mechanics. So the simplest version of this is you have R2n, which is a phase space. It has n position coordinates x1 through xn and n momentum coordinates y1 through yn. And then you take a Hamiltonian function h, and that determines the equations of motion of your physical system, where if you have xi and yi evolving in time, then the time derivative of xi is the partial derivative of h with respect to yi. The time derivative of yi is minus partial derivative of h with respect to xi. And you can also say that you're just looking at this Hamiltonian vector field. So as your system evolves in time, your point in phase space follows this vector field. And one of the most basic questions you can ask in dynamics is what are the periodic orbits of this vector field? So we're interested in periodic orbits of Hamiltonian vector fields. And well, without assuming anything, we can't say very much, but maybe under some assumptions, what can we say about the periodic orbits? And just to remark about what this problem means exactly. So first of all, the Hamiltonian vector field can be described more concisely by this equation, which says that if you take the standard symplectic form in R2n, sum of dxi dyi, and you insert the Hamiltonian vector field, then you just get the derivative of h. And then there are a couple of immediate consequences of that. So first of all, the Hamiltonian vector field preserves h. This is conservation of energy. So you always move along a single level set of h. And second, what you're doing on this level set of h actually just depends on the level set and not h. So if y is a hypersurface, which is a regular level set of h, that means the derivative of h is non-zero on it. Then if you take any other Hamiltonian, which also has y as a regular level set, then the vector field will be the same up to scaling. And this vector field always lives in a one-dimensional foliation of y, which is the kernel of omega restricted to y. So really, this is just a question about hypersurfaces in R2n. So you could say, if I have a hypersurface, what can I say about periodic orbits? Now, to discuss this question, it helps to rephrase it in a more general language. So let me start over. Okay, so we're going to start with an odd-dimensional manifold y, which you could think of as a hypersurface in R2n, but it could be more general. And a contact form in Y is a one-form lambda such that lambda wedge d lambda to the n minus 1 power never vanishes. And if you have a contact form, then it determines two things. So its kernel is a codimension 1 subbundle of the tangent bundle. And there's also a Reeb vector field R. And this is in the kernel of d lambda. So this equation implies that the kernel of d lambda is one-dimensional. So R is in the kernel of d lambda. And we also normalize it by saying that lambda of R is equal to 1. And we're interested in periodic orbits of the Reeb vector field, which we call Rave orbits for short. So formally, it's a map from a circle given by the real numbers modulo some number t to y, such that the derivative of that map equals the Reeb vector field. And so its image is some circle in y, which is everywhere tangent to the Reeb vector field, but you're allowed to go around the same circle multiple times. So the Reeb orbit is called simple if you only go around the circle once. And otherwise, it's a default cover of a simple Reeb orbit for some positive integer. And I also define the symplectic action of the orbit to be the period. And because the Reeb vector field, because the Reeb vector field is normalized so that lambda of R equals 1, it's equivalent to say you just integrate lambda over the orbit. And what does this have to do with what we were talking about before? Well, a basic example is, well, not every hypersurface in R2n, but if you take what's called a star-shaped hypersurface, so if this is R2n, we take a hypersurface like this, so let's call this Y, which is transverse to rays coming from the origin. And if Y is a star-shaped hypersurface, then you can do a little calculation to see that if you take this one form, lambda, so it's a half sum of xi dyi minus yi dxi. The motivation for writing down this one form is that it's a primitive of omega. So if you restrict this to y, then it's a contact form. And you can also check that the Reeb vector field in y is the same as the Hamiltonian vector field for any Hamiltonian having y as a level set, up to scaling. So for star-shaped hypersurfaces, the periodic orbits of the Hamiltonian vector field on there are a special case of Reeb orbits. And sort of the starting point for what I'll talk about today is a theorem of Rubinowitz, who proved that every compact star-shaped hypersurface has at least one Reeb orbit. Another example of contact forms comes from looking at geodesic flows. So if you have a smooth manifold, so this is now n-dimensional instead of 2 n-dimensional. So if I have an n-dimensional smooth manifold, then on the cotangent bundle, there's a completely canonical one form. So it's a little confusing if you've never seen it before, but well, what I have to do is I have to input a tangent vector to the cotangent bundle and output a number. So how do I do that? Well, I have a point in the cotangent bundle. I have a tangent vector to the cotangent bundle. So I can project that down to m to get a tangent vector to m. And I also have a cotangent vector to m, and then I just pair them. So it's a completely canonical form. And its derivative is a canonical symplectic form. And you can check that if you have a Riemannian metric on M, then you can look at the set of cotangent vectors of length 1. This is now a 2n minus 1 dimensional manifold. And lambda restricts to a contact form on it. And the Reeb vector field on this exactly gives you the geodesic flow. So sort of downstairs, you're following geodesics. And also the symplectic action Right, so the Rave orbits correspond to closed geodesics. You have to choose a direction. If you go the other direction, that's a different Rave orbit. And the symplectic action is the same as the Riemannian length. And it's an old theorem of Lusternik and Fett that if you have a compact Riemannian manifold, there's at least one closed geodesic. Of course, there are many newer theorems giving more geodesics. So now let's talk about what's known about existence of Rave orbits. So I just showed you a couple of examples where Rave orbits are known to exist. And motivated by those examples and a couple of other examples, Weinstein formulated the Weinstein conjecture, which says that every compact manifold with a contact form has at least one Rave orbit. And there's a long history of work on this and various results. So I'm going to have to skip most of it due to lack of time. So one nice result was Hofer proved in 1993 that in the three-dimensional case, if you have the three-sphere, or if pi2 of the three manifold is non-zero, or if the contact structure is what's called over-twisted, don't worry about what that means, then there's a Rave orbit. In fact, there's a contractible Rave orbit. And later, in 2006, Taubes proved the Weinstein conjecture in all cases in 3 dimensions. So for every compact 3-manifold with a contact form, there's at least one Rave orbit. And you can also say a little bit about homology classes of Rave orbits. In higher dimensions, it's an open question. There are some special cases, but it's pretty open. All right. Now, there are various ways we could try to improve this. So one way is to try to say something about the properties of the Rave orbits, not just say that a Rave orbit exists, but say that a Rave orbit exists with this or that property. But one of the things you could try to do is to make the period small. So you could try to prove that there exists a Rave orbit with some upper bound on its period in terms of something else. There's a fascinating conjecture of Viterbo, which says that if you take a star-shaped domain in R2n, which is not only star-shaped but also convex, then there exists a Rave orbit whose period is small with respect to the volume of the domain. In other words, if y is the boundary of some domain, so y is the boundary of x, and x is convex, then well, actually, the worst case is where it's a ball. So if I have something which is not a ball, then it has a Rave orbit which has shorter period or equal period than a ball of the same volume. Another thing you could try to do is extend the class of vector fields for which you can prove that a Rave orbit exists. So for general smooth vector fields, you can make examples with no periodic orbit at all. So what exactly do you need to guarantee a periodic orbit? So in a joint work with Taubes, we proved that in the in the three-dimensional case, you can slightly generalize to what's called a stable Hamiltonian structure in most cases. And the focus of my talk today is a third way you can try to generalize, which is try to prove that there's more than one Rave orbit. So for example, there's an old conjecture which says that, I don't know who said it first, but it says that every compact star-shaped hypersurface in R2n has at least n Rave orbits, n simple Rave orbits. So that's known in when n equals 2, so in 4 dimensions, but not in higher dimensions. So let's do an example to see what's going on here. So instead of talking about R2n, let's talk about Cn. So we'll denote its coordinates by Zi. So xi and yi are the real and imaginary parts of Zi. So one basic example of a hypersurface you can look at is the boundary of an ellipsoid. So we fix some positive numbers a1 through an. We look at this ellipsoid, set of complex vectors such that the sum of pi times absolute value of zi squared over ai is less than or equal to 1. Its boundary is a nice star-shaped hypersurface. And you can compute the Rave vector field. You can just take this function to be the Hamiltonian and compute the Hamiltonian vector field of that. And then rescale it. And you find that what the Rave vector field does is it rotates each of the complex components zi. So d by d theta I means that I'm just changing the argument of zi. So it changes the arguments of all the components, but at different speeds. So it takes time ai for the ith coordinate to go once around. So if all but one of the coordinates is 0, then you will get a periodic orbit whose period is ai. If two of the components are non-zero, then if the ratios between these numbers ai are irrational, then you can never come back to where you started. So if these ai over aj are irrational, that gives you an example with exactly n simple Rave orbits. So the conjecture in the previous slide is sharp. Now, to state more theorems, I need to make one more definition of a non-degenerate contact form. So basically, non-degenerate means that the Rave orbits are cut out transversely in an appropriate sense. So if I have a Rave orbit, I can take a normal plane to the Rave orbit in the tangent space at a point in the Rave orbit, and I can look at the linearized flow. So basically, you start at a point near the orbit, you flow until you come back here. So that gives you some map from a disk around this point to itself. You take the derivative of that map at 0. That gives you a linear map from this plane to itself. And the orbit is called non-degenerate if 1 is not an eigenvalue of that map. So that in particular implies that the Rave orbit is isolated in the loop space. So I say that the contact form is non-degenerate if all Rave orbits have this property, and one can show that this is true for generic contact form. It's like in the ellipsoid example, if ai over aj is irrational, then it's non-degenerate. If ai over aj is rational, then it's degenerate. So a theorem of Hofer-Wysocki-Zehnder says that on the 3-sphere, if I have a contact form which is non-degenerate, they also assume that it satisfies an additional genericity property. And if its contact structure is the standard contact structure in S3, equivalently you could say that I take a generic star-shaped hypersurface in R4. Then there are either 2 or infinitely many simple Rave orbits. And another theorem by Colette and Honda says that for a complicated 3-manifold, the precise definition of complicated is kind of a mouthful, so I won't say that. But anyway, for a complicated 3-manifold, then there are infinitely many Rave orbits. So this is something about simple 3-manifolds. This is something about complicated ones. In a joint work with Taubes, we showed that if I have a non-degenerate contact 3-manifold, then there are always at least 2 simple Rave orbits. And if the 3-manifold is not the 3-sphere or a lens space, then there are always at least 3 simple Rave orbits. And in a work with Dan Christopher Gardner, which makes heavy use of a work with us and Vinicius Ramos on well, I'll tell you about that result later. So we proved that even in the degenerate case, there are always at least 2 simple Rave orbits. And in fact, it's not known if there's any example where there are more than 2 simple Rave orbits, but not infinitely many. Every time I give a talk, at the end of the talk, somebody tells me they have an example. and then I check it and it doesn't work. Okay, so now I can state the main result that I wanted to tell you about. So this is a joint work with Dan and Vinicius. Sorry, not Dan and Vinicius. This is a joint work with Dan Christopher Gardner and Dan Parmigliano. So it says that if I have a closed connected three-manifold with a contact form, I need to make two assumptions. First, the contact form is non-degenerate. And second, the first Chern class of the contact structure, the kernel of lambda, is torsion in the second cohomology of Y. So this is automatically true, for example, if Y is a rational homology three-sphere. So under those two assumptions, there are either two or infinitely many simple Reeb orbits. And if you combine this with the result of Taubes on the previous slide, you get a corollary, which is that in most cases, actually, there are infinitely many. Because we showed that in the non-degenerate case, if it's not S3 or a lens-based, then there are at least three Reeb orbits. So then there have to be infinitely many. So if I have a three-manifold with a non-degenerate contact form, and the contact structure is torsion, and it's not S3 or a lens-based, then there are infinitely many Reeb orbits. That's the statement. So how on earth do you prove things like this? So I want to tell you two basic strategies for trying to prove the existence of Reeb orbits. The proof of the main theorem actually combines both of them. So the first strategy is using what's called contact homology. So the idea is you think like a topologist and say, I'm just going to count the Reeb orbits. I'm going to define some count. I'm going to prove that this count is non-zero, and then it's a topological invariant, and then I'm done. So a model for this would be something like the Lefschetz fixed point theorem. If you have a map from a topological space to itself, if the Lefschetz number is non-zero, then it has to have a fixed point. In the case of Reeb orbits, that doesn't work so well because, as you saw, we're trying to prove that there are infinitely many orbits, and that seems to be true most of the time. So you can't really count infinitely many orbits very easily. Instead of just saying, 1, 2, 3, 4, 5, blah, 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 you have to do something a little more sophisticated. So the idea introduced by Eliashberg, Giventhal, and Hofer is you define a chain complex, and it's generated by Reeb orbits. Actually, you have to throw out a few bad ones. So it's generated by simple Reeb orbits. And then there's going to be a differential which counts holomorphic cylinders in R cross Y. So this denotes the R direction. So here's R cross Y. I have one Reeb orbit up here and another Reeb orbit down there, and there's some kind of cylinder going between them, a J holomorphic cylinder. And you count these to define a differential on the chain complex. So the idea is that if it's just one of these holomorphic cylinders, then maybe those two Reeb orbits could get canceled if you deform the contact form. And when you take the homology, you get something which is invariant. So even though many Reeb orbits could get created and destroyed if you change the contact form, if the homology is non-zero, then there always have to be some Reeb orbits left. So you define this homology, and that's what's called cylindrical contact homology. So if you're being careful, it turns out there are some serious technical issues in defining this rigorously. So there are transversality problems with holomorphic curves. It's known how to do this in some cases. In other cases, it's still a work in progress by a number of people. Now, we can use contact homology to prove that there are lots of Reeb orbits. So the first thing you might think is that, well, let's just prove that the contact homology is infinite rank, and then we know that there are infinitely many Rave orbits. But that's a mistake, because remember that Rave orbits can be multiply covered. So really, we just want to count simple Rave orbits. And if you have one simple Rave orbit, then you already have infinitely many Rave orbits, which are covers of it. So you need to do something a little fancier. So one way is using the action filtration. So it turns out that if there's a holomorphic cylinder like this going from one Rave orbit to another, then the symplectic action of this orbit is bigger than the symplectic action of that Rave orbit. So this chain complex has a filtration by the symplectic action. And that means that for any real number L, if I just look at the span of Rave orbits of action L, that's a subcomplex. And it has a well-defined homology, which we'll call filtered contact homology. We could call it CHL. And then the trick is to see how that grows as a function of L. So what Colette and Honda do is they show that in their situation, where they have these complicated three manifolds, the rank of CHL grows exponentially with L. And that really does imply that you have infinitely many Rave orbits, because if you had only finitely many, the rank of this could grow at most polynomially in L. And similarly, the theorem with Dan Christopher Gardner that I stated before, showing that there are always at least two simple orbits, uses a different kind of contact homology called embedded contact homology, and shows that its rank grows quadratically in the action. And that implies that there are at least two orbits. If you could prove that it grows cubically, then you'd have at least three orbits. So this is sort of the most direct approach to finding Rave orbits, to detect them with some kind of homology theory. Now there's also a more indirect approach, and this is what Hofer, Wazowski, Sander use in their proof of two or infinitely many orbits on the three-sphere. And this approach involves constructing a genus zero global surface of section. So what's that? So definition, a global surface of section for the Rave flow, I'll draw a picture. So it's a surface in the three manifold with boundary, and the surface is embedded, except its boundary circles might just be immersed. So here's my surface, sigma. And we assume that each boundary circle is a Rave orbit. And for any other point in the three manifold, if you follow the Rave vector field forward in time, you will eventually hit sigma. And if you follow the Rave vector field backwards in time, you'll also hit sigma. And in particular, there is a return map phi from the interior sigma to itself. So you start at a point in sigma, what's called z. You follow the Rave flow. You come back to some other point. Let's call it phi of z. So that's a map from the surface to itself. If I have a periodic orbit of that map, meaning a fixed point of phi to the k for some k, but that gives me a modulo applying phi to it, then that's a Rave orbit, a closed orbit of a periodic orbit of this vector field. And because it's a surface of section, that's all the Rave orbits there is. So every Rave orbit is either one of these circles on the boundary of sigma, or it's a periodic orbit of this map phi. Nothing else is possible. So that reduces the problem of understanding the dynamics of this three-dimensional vector field to understanding the dynamics of a map on a two-dimensional surface. That's still difficult, but it's less difficult than it was before. And in particular, there's an important theorem of Frank's, which one can use. So the theorem of Frank's says that if I have an area preserving homeomorphism from an open annulus to itself, then either it has no periodic orbits or it has infinitely many. And as a corollary, if I have a genus 0 global surface of section, then there are either 2 or infinitely many Rave orbits. And why is that? Well, if the surface of section is an annulus, then I could apply Frank's theorem directly. I have 2 Rave orbits on the boundary, plus in the interior of the annulus, I have either 0 or infinitely many Rave orbits. So 2 plus 0 or infinity equals 2 or infinity. That's all the arithmetic I can do. If the surface has more boundary components, then you can collapse some of them to points until you have an annulus. Then you'll still have a homeomorphism. So it's very fortunate that Frank's theorem only requires the map to be homeomorphism and not a diffeomorphism. And if your surface has only one boundary component, there's a trick you can do using the Brewer translation theorem. So this is how Hofer, Wysocki, Zander proved the result. They found a genus 0 global surface of section and then applied Frank's theorem. So here's the outline of how we prove our theorem. So we start with a closed connected 3-manifold. We assume that the contact form is non-degenerate and that C1 of the contact structure is torsion. I need to prove that there are either 2 or infinitely many Rave orbits. Without loss of generality, I can assume that there are only finitely many Rave orbits. And then it's enough to find a genus 0 global surface of section. And we can do that. So the idea is to use embedded contact homology, which I'll tell you about in a bit, to find a genus 0 global surface of section. So embedded contact homology will produce lots of holomorphic curves in R cross Y, and we'll show that at least one of those holomorphic curves in R cross Y projects to a curve in Y, which is a genus 0 global surface of section. And just to clarify, I am not proving that there's always a genus 0 global surface of section. That's not true. I'm just showing that if there are only finitely many simple Rave orbits, and these other assumptions hold, then there's a global genus 0 global surface of section. Okay, so now I have to tell you a little bit about embedded contact homology, which is what I use to get this surface of section. It's going to get a little more technical. So there's a lot of stuff that goes into this, but I just want to give you the basic idea. So just don't read any of the formulas. Or maybe I should ask if there are any questions before I start getting into that. Okay, well, here we go. Oh, yes? So you can't always find the globus. Yeah. Yeah. Well, it might exist. Sometimes it does. For example, on the 3-sphere, you usually can find these, but in general, it might not exist. I believe a counterexample is the geodesic flow on a hyperbolic surface. Good. Okay, so J holomorphic curves. So what are those? So you choose an almost complex structure in R cross Y. So that's just a map, J, from the tangent bundle of R cross Y to itself, such that J squared equals -1. And we assume a few things which are standard in contact homology. So I assume that J of the derivative of the r direction is the Reeb vector field. I assume that J sends the contact plane to itself, rotating positively with respect to d lambda, and J is invariant under translation. And you also want to assume that it's generic. And then we're going to look at holomorphic curves in R cross Y. So when they're embedded, you can think of them as just embedded surfaces in R cross Y, such that J sends the tangent space of the surface to itself. And we're going to look at holomorphic curves more general than cylinders that converge to some Reeb orbits as the r coordinate goes to plus or minus infinity. But there could be several, and these curves could have higher genus, so they could look like this, for example. So here's a genus 1 holomorphic curve that goes to 3 Reeb orbits as the r coordinate goes to plus infinity, and to 2 Reeb orbits as the r coordinate goes to minus infinity. And there are lots of these holomorphic curves, and I want to count them in some sensible way to get some useful information. So one thing we can do is talk about embedded contact homology. This is not the most general theory. There's a zero here, which means we're looking at the sort of the simplest case. So it's generated by not by single Reeb orbits, but by finite sets of Reeb orbits. So you have a finite set of simple Reeb orbits with some positive integer multiplicities. And we assume that the total homology class in H1 of Y of this set of Reeb orbits is 0. That's what this 0 is. You can also look at cases where this total homology class is something else, but I don't want to do that today. There's also a technical assumption that hyperbolic orbits could only have multiplicity 1. And then there's a grading on this chain complex, which is an integer value grading. It's some complicated formula. Just ignore it. Or you can look at it if you want. Anyway, so there's a complicated formula for the grading. And the differential, so I'm using Z mod 2 coefficients. And if I input a generator alpha and apply the differential to it, I get a sum over generators beta. And the coefficient of beta is a count of holomorphic curves going from alpha to beta. So you have alpha up here and beta down there. And we actually call them holomorphic currents. That's sort of a technical fine point. And you can show that this is a chain complex, and the homology is the embedded contact homology. And what's even more important for the talk today is that there's a map on this called the U map. And this map decreases the grading by 2. And it's defined like the differential, but instead of just counting holomorphic curves from alpha to beta, I also require these holomorphic curves to go through some point. So I pick a base point Z in R cross Y, and I count curves. So now this grading difference is 2 because these curves will live in 2-dimensional moduli spaces. And I require them to go through this point Z, which puts a codimension 2 constraint on them. So I get some finite count of curves. And this count gives me a chain map, which induces this U map. So that's the basic structure. So the differential counts these curves, which live in 1-dimensional moduli spaces, and you mod out by R translation to get a finite count. And the U map counts these curves in 2-dimensional moduli spaces that have a point constraint. Whoops. Okay. And now we have to bring in some nuclear weapons here, which is Seiberg-Witten theory. So continuing to make our same assumptions, one can show that there exists what I call a U sequence. This is an infinite sequence of classes, sigma k, such that each sigma k is U of sigma k plus 1. So just if I draw these algebraically, here's sigma 1, and here's sigma 2, and here's sigma 3, and so on, and the U map goes like this. And it goes up infinitely. And the way to prove this is you have to combine two very non-trivial things. So the first is that Taubes proved that embedded contact homology is canonically isomorphic to a version of Seiberg-Witten Floer cohomology of the three-manifold, as defined by Kronheim and Mrufka. And the proof of that is a 500-page series of papers. And second, once you know this, you can take any facts you know about Seiberg-Witten Floer homology and carry them over to say things about embedded contact homology. And in particular, Kronheim and Mrufka proved an analog of this statement for their Seiberg-Witten Floer cohomology. So you can read their 800-page book, which explains how to construct Seiberg-Witten theory and prove this and many other things. And so then you combine that and you get this lemma. So that's the input from Seiberg-Witten theory, without which we wouldn't be able to do anything. Okay, so now, with all that machinery, how can we start looking for a global surface of section? So here's what we're doing. So continuing to try to prove my main theorem on two or infinitely many Rave orbits. So the assumptions, lambda is a non-degenerate contact form in a closed connected three-manifold. First term class of the contact structure is torsion. I know that there's a U sequence from the previous lemma. And that means that for each k, there is a holomorphic curve which is counted by the U map from sigma k plus 1 to sigma k. So this is very important. So each one of these arrows tells me that there exists some holomorphic curve. And this is really, for the kind of symplectic geometry I do, this is the essence. So I sort of didn't make a slide, but here's a sort of symplectic geometry for dummies. Well, not all symplectic geometry, but the kind of symplectic geometry that uses holomorphic curves. So the way it works is, one, you prove that a holomorphic curve exists. And two, you conclude something. Okay? So that's the is sort of, for the kind of symplectic geometry that involves holomorphic curves, that's how it works. So whenever you prove existence of a holomorphic curve, that's good. You could try to make some geometric conclusion from this. So this sort of, right, okay. So anyway, now I have this whole supply of holomorphic curves, which is provided magically by Seiberg-Witten theory. What I want to show is that at least one of these holomorphic curves actually gives me the global surface of section that I want. Now these holomorphic curves live in R cross Y, but you can project them to R cross Y, you can project them from R cross Y to Y. And if you're very lucky, that projection will be an embedding into Y. If you're even luckier, it will be a global surface of section. And what we're going to try to do is show that with these infinitely many curves, we can show that at least one of them has this property. So what would we need to do to get that? So note that a curve counted by the U map is divided into two parts. So C1 is the interesting part. So maybe it looks like this in the picture. I'd be happier if it had genus 0, but I'm trying to get a genus 0 global surface of section. And then there might be some additional cylinders, which are just r across a Rave orbit. And these are not very interesting, but they can be there. So that's what one of these curves look like. And we have a little proposition which tells us when we get a global surface of section. So there are various assumptions. So let C be the non-trivial part of a holomorphic curve counted by the UMAP. So assume it has genus 0, which we wanted anyway, because we're trying to get a genus 0 surface of section. And assume some other stuff. Then the projection of C to the 3 manifold is an embedding, which is the interior of a global surface of section. So we need to show that one of these curves has genus 0 and also satisfies these other assumptions, which I'll skip over for now. So the emphasis is how do we get this thing to have genus 0? So first I should tell you what's involved in the proof of the proposition. So how do I know this thing is going to give me a genus 0 surface of section? Well, from the theory of ECH, the holomorphic curve is embedded in r cross y. And I want to prove that it's still embedded after I project it to y. And the main part of that is to show that that projection is injective. And to prove that that projection is injective, what you want to show is if you take the curve and you translate it in the r direction, then what you get is disjoint. So the curve does not intersect, it translates in the r direction. That's equivalent to saying that the projection is injective. How do you prove that it doesn't intersect as translates? Well, you can do an algebraic count of the number of intersections of this curve with the translate. And if you use the assumptions in the proposition, you find that that algebraic count is 0. And then there's a very important property of holomorphic curves in 4 dimensions, which is that they always intersect positively. If they intersect at isolated points, then the intersections count positively. So if the algebraic count of intersections is 0, then they're disjoint, unless they're the same curve. So that gives you an embedded curve, and then using the additional assumptions, you can argue that it actually gives you a genus 0 global surface of section. So how do we get genus 0? Well, I didn't explain the grading in ECH, but there's another number, which I call J0, which is defined similarly to the grading. And the significance of this number J0 is that it gives you a bound on the genus. So you have this proposition which says that J0 of C is minus the Euler characteristic of the non-trivial part, plus some additional non-negative terms. So what that means is if you can show that this J0 of C is small, then that's going to give you an upper bound on the genus of C. I'm skipping over this so I can get to the most interesting part. So basically I have this some number here, and I want to bound this number. And this number is similar to the grading. The difference between the grading and this number is, well, it's this stuff, which I didn't explain. But this stuff is you can bound it in terms of the symplectic action. So if the symplectic action is not too big, then this number J0 is close to the grading. And all of the curves, these U curves that we're counting, have grading difference 2. And that means the holomorphic curves, we expect to have J0 close to 2. So let me tell you the most interesting part, which is what allows us to control this. So this is what's called the volume property of ECH. So it's a relation between the symplectic action of Rave orbits and the volume of the contact manifold. And here's the statement. So this is a joint work with Dan and Vinicius. So suppose I have a U sequence. Now, for each of these classes, sigma k in the U sequence, I can say, what is the minimum symplectic action needed to represent that class? So remember, the chain complex has a filtration by symplectic action. And I can represent this class by a cycle in the chain complex. So it's a sum of a bunch of generators, each of which has some action. I want to make the maximum action as small as possible. So I define C sigma k to be the smallest L such that the class sigma k can be represented by a cycle, which is a sum of generators, all of which have action less than or equal to L. And the theorem is that these numbers C sigma k satisfy an asymptotic formula, which is that the limit of C sigma k squared divided by k is equal to 2 times the volume. And the volume, by definition, is the integral of lambda wedge d lambda over the 3 manifold. And the significance of that for us is that this C sigma k grows like the square root of k. We don't really need to know that it's exactly in terms of the volume, although there are some other applications. So there's a beautiful work by Asymptotic and Irie, who used the exact relation with volume to prove a C infinity closing lemma for Hamiltonian diffeomorphisms of surfaces. Anyway, so this tells us that these things grow like the square root of k. So how do we use that? So this is the outline of the rest of the proof. Okay, so I have a U sequence, and I take a large number n. I take a cycle representing the class sigma n, and I can choose that cycle such that this chain map that induces a U map to the n minus 1 is non-zero on some generator in the cycle. So that means that I have this diagram not only on the homology level, but on the chain level. So I have, where am I going to draw it? So here's alpha of 1, alpha of 2, and so on up to alpha of n. And I have a chain of holomorphic curves going between these generators. Now, each of these holomorphic curves has grading difference I equals 2. So the total of I in this whole chain is 2n minus 2. Now, you could then say, what about the total j, the total j0? Well, it's going to be approximately the same thing, plus some error term, but because of the relation between ECH capacities and volume, this error term is bounded by the square root of n times some constant depending on the volume of the 3 manifold. So if n is large, then most of these curves are going to have j0 equal to 2. And that basically gives us enough control over their topology to show that one of these curves will have genus 0 and satisfy the other assumptions in the proposition, which are needed to get a global surface of section. So that's the idea of the proof. So the key ingredients are We use Seiberg-Witten theory to get this chain of holomorphic curves counted by the UMAP. We use the relation between ECH and volume to get some control of the symplectic action involved here. Then that allows us to control the topological complexity of these curves to get a genus zero global surface of section, and then we can apply Franks' theorem to conclude the theorem. That's the idea. And then you could say, could we generalize this? Could we remove any of the hypotheses in the theorem? So, well, one hypothesis was that C1 of the context structure is torsion, so that seems kind of mysterious. Doesn't seem to have any geometric relevance to dynamics. Where did we use that? Well, I didn't explain it in detail, but it comes into controlling this number J0. So if I don't know that C1 is torsion, then I don't have any control over this J0, at least not without doing something more. And so I can't get a genus zero global surface of section. It's an interesting problem for future research to try to figure out what to do if you don't know that C1 is torsion. And the assumption that lambda is non-degenerate is used all the time in setting up the machinery. Could maybe be removed with some technical work. And we could also say, what about higher dimensions? So I don't even know what is supposed to be true. There's a very recent preprint by Albers, Geiges, and Samish, which shows that in the 5-dimensional case, for example, you can find a contact 5 manifold with any number of simple Rave orbits, as long as it's at least 3. Maybe if you fix the contact manifold, you could say more. Right. So that's all that I wanted to tell you about. Thank you.